I'm going to write the formal definition of a derivative. It's the limit as h approaches 0 of the function evaluated at a plus h minus the function evaluated at a all over a plus h minus a. That's the definition, the formal definition of a derivative. Now what I want to do is to show you how we come about this definition. If we take a curve, so let me just draw an arbitrary one. There it is. And let's label this the f of x axis, and this is the x. This is a function. It passes the vertical line test. And let's label this coordinate as a. Let's assume that we go out a distance h more than what a is. This coordinate right here, this x coordinate, would be a plus h. Just like, let's say if this was 5 and we want to go 2 more, this would be 5 plus 2 more would be 7. This is 5, this number would be 7. We're going 2 more than what 5 is. If we would plug this value into the function, remember this is the function, we would start to evaluate this function at a, and the number that we would get is this value right here, which would be f of a. Because when we put a into the function, we're going to get the y value that is associated with that input. That x will give us this y. Likewise with this a plus h, when we plug it into the function, we'll get this, which is f of a plus h. Now what I'm going to do is to draw a triangle, and if I were to connect these 2 points by a straight line, and picture that this line goes through those points, it really would be like a secant line. A line that goes through those 2 things and continues on. I know I drew it a little bit sloppy, but bear with me. If we make this triangle, I'm doing dashed lines here, I want to know what this height of the triangle is. So if you think about it, the height, the distance between this corner and that point right here, this corner right here, we made a 90-degree triangle. This would be f of a plus h minus f of a. It'll be this y coordinate minus this y coordinate will give you how much that is. Let's say if this was 10 and this was 8. 10 minus 8 would give you 2. So that's what the height of that triangle would be. This piece, this length right here, the base of that triangle, would be, take this coordinate, a plus h, and subtract this one from it. And look what happens. A minus a cancel, and we're left with h, which it should be, because we said that the distance between these 2 things is just h, and that's what that would be. The way that we get this thing is the line that goes through this has a slope, and remember the slope formula. Slope equals y2 minus y1 over x2 minus x1. But in this case, this is the y2 minus y1. So we have f of a plus h minus f of a all over x2 minus x1. So it's a plus h minus a. This is exactly what we have over there. Now how does the derivative come into play? What we're trying to do is to find the slope of the tangent line at that point. So what's going to happen is we're going to slowly bring this point in to get closer and closer to this one till it really becomes that point. They're superimposed on top of each other. As we would bring this point in on that curve, this h that we're adding to this a would approach 0. H would become 0 because as we're adding 0, we would be coming closer to a. We're not adding anything to a if we get to a point where h is actually 0. So what we're doing is we're letting that h approach 0. That h is getting smaller and smaller. So this point is really coming closer to that one. And this is the slope. So what we would have is eventually the slope of the tangent line at that point. And that's what we're looking at when we find derivatives.